Welcome back. Today we begin a two-part series on artificial intelligence and the brain. In particular, we will contrast a question, namely, what is a thought? Have you ever seen a thought? Can you define clearly what a thought really is? This series of talks was inspired by a presentation given by Geoffrey Hinton, who is the inventor of the neural nets and especially the backpropagation algorithm, which has revolutionized artificial intelligence and changed the way we think about AI and its influence in the world. So first I will give you an introduction into just the scale of AI and what we are dealing with. And here in the first slide, you can see the big neural network that we all share, namely the human brain. If you count the neurons in the brain, you wind up with as many neurons as there are trees in the Amazon basin. And if you count the connections in the brain, you have as many connections in the brain as there are leaves on the trees in the Amazon. That gives you a sense of the scale of the computing power and the intricate structure of the brain. And we will now, as we go forward, draw some parallels between brain structure and function and how AI is working at this particular time that we experience right now. So here then is a neuron. And you know it's pretty complicated. We have a cell body, the axon goes here, and there are terminals that terminate at the postsynaptic membrane. We also have dendrites, which have a lot of computing power and contain synapses as well. Now, it's very difficult to copy in software a model of a neuron. It has been attempted by Dr. Makram at the Eidgenössische Hochschule in Geneva and Lausanne, Switzerland. We have mentioned this in a previous talk. However, what AI does is a highly simplified version. Namely, we have a bunch of inputs which synapse, quote unquote, on a node or a target cell. And all you want to do is, there are different weights associated with these inputs. And mathematically, you count all the weights, and if they exceed a certain threshold, then the neuron will fire. And you see this here. Once the weight exceeds the threshold, you get a signal transmitted. So this is kind of the basic idea of copying elements of brain function into the thinking of artificial intelligence. Now, what is this? This is a data center. It looks humongous, and there are many of these in the world now. They use the power of an entire small city and maybe a medium-sized city to get their servers going. And here in the next slide, you see that the data center is being enhanced. See, this is what you saw before. And all this will be built out in short order. So it's a tremendous growth of data collection in the world. And AI critically depends on the availability of massive amounts of data to train the AI systems, the neural networks that constitute the machine learning aspect of AI. So here then is a presentation that some people gave at Google, and it has to do with the human parity in speech recognition, which was recently achieved. Speech recognition is a very difficult task for an AI system to implement, and people were stuck at a 25 or 26% error rate for many, many years until AI was totally revamped by the introduction of the recurrent networks that Dr. Hinton has really originated. Another aspect is playing games. Now, this is the game of Go, a game that is 3,000 years old. So there is massive human experience in what the game of Go is all about. It only has two rules. Rule number one is, if you can encircle a space, you are the white player, where the black player cannot get into, then you own this territory and you count all these squares, and that is your score, your points. The other rule is that if you encircle the opponent's stones, like here, you can take them out of the game and you add another 3 points to your score. These are the only two rules. Very, very simple. But as it turns out, this game has great depth, having to do with strategic thinking, geometry, predicting your opponent's move, and just a depth of experience that is 3,000 years deep. So here then is a game of Go, and you can see that white is doing pretty well here and catching a bunch of territory. Here is another area of territory, and black is carving out territory over here. And you can see sometimes games are decided by 1 point or a very small number of points. So here is a reference to an incredible move in move 78 in game 4, and we will get back to this. Sedol is the world champion 10 or 20 times over now from Korea, who has ruled this game, and nobody really has been able to touch him until he played an artificial intelligence program called AlphaZero, developed by the Google company based in London, an offshoot of Google specializing in artificial intelligence. So I will now show you a series of brief videos which were shot in Korea during the encounter between the AlphaZero program and Sedol. And you can see in the clips that Sedol was quite confident that he could beat AlphaZero because it's just a program or a set of algorithms, whereas he, the world champion, has human intuition. And he was betting that human intuition would always beat a pure machine algorithm. And you can see in the videos that his hopes were disappointed. He, in fact, lost the first game, and he was totally stunned. It affected his psychology, where in the next few games he changed the way he played, which was not quite natural to him. And it was only down the road in game 4 or so that he was able to win one game. But the end result was AlphaZero 4, Sedol 1. And that has now revolutionized artificial intelligence because it is believed that Go is the most complicated, the most demanding game yet invented by man.
That it was decades away. Some people thought it would be never because they felt that to succeed at Go you needed human intuition.
Go is the world's oldest continuously played board game, and in some sense it is one of the simplest and also most abstract.
There's only one type of piece, there's only one type of move, you just place that piece on the board, and then your goal is to create a linked group of your stones that surrounds some empty territory. And when you surround enemy stones, you capture them and remove them from the board. You earn points by surrounding territory, and at the end of the game, the person with the most territory wins.
여기는 이런 감각들을 컴퓨터인 인공지능이 따라오기에는 약간 무리가 있지 않나 이렇게 생각을 해서 제가 꼭 인간의 그런 걸 지켜낼 수 있도록 최선을 다하겠습니다.
All the world gave the pressure to Sedol. Before this, he played the tournament for country, for himself. But this time, he played for the human.
아직은 기계가 사람을 바둑에서 이기진 않았으면 좋겠어.
So in the meantime, artificial intelligence has progressed further. Now there is reward learning introduced are algorithms, and they are universal in such a way that you don't need to teach the machine very much. Let's go back one slide, whereby there's no bootstrapping on human data. It starts completely from random play with zero knowledge. It plays against itself millions of times, and it learns incrementally from its own mistakes. It gets stronger and stronger as time goes on. So you know that computer chess, a number of years ago now, was able to beat Garry Kasparov in a famous series of games. This is an IBM computer called Deep Blue. However, that artificial intelligence system was based on rules and logical inference and deep searches. It was not based on the neural net architecture that we will be discussing today. So here are some aspects of all the different items that go into a chess engine. Heuristics, all kinds of mathematical and search parameters. It's a very, very complicated way to do this, and Deep Blue was a huge machine, as you saw in the image. Whereas when AlphaGo went to Korea, the program was housed on a laptop. So AlphaZero, which is now the new implementation of AlphaGo, has no opening book, no endgame database, no heuristics, starts with random play, and uses the same algorithm with some hyperparameters in all games. So AlphaGo also took a stab at chess, and you can see here that it won against a leading chess program 28 times and had a draw of 72 with 0 losses. Shogi is another very difficult board game, and AlphaZero again did very well with a few losses. And AlphaZero versus AlphaGo Zero is a 60 and 40 score. So AlphaGo Zero, after 3 days of playing against itself, was able to win almost 50% of the games against AlphaZero. So this new reward learning algorithm promises that human training or human facilitated training may not be necessary, but the machine with very little instruction can learn what it has to do by itself. And here's the learning curve. So you can see that after 4 hours, AlphaZero surpassed the stockfish in chess, and after 200 steps, AlphaZero surpasses AlphaGo Lee, which is the program that won against Lee Sedol. And here is Shogi, and you can see that very quickly AlphaZero was able to match that game as well. So this is the number of searches that are required in a typical chess engine, namely 10 million moves, whereas AlphaZero only searches to the depth of 10,000 of moves using its algorithm in the distributed neural network. So AlphaZero, the style it uses is it doesn't play like a human. It has no concept of materiality. It doesn't care if it loses a stone. Humans respond to material loss in chess and in Go with some emotion. AlphaGo does not respond at all and rather looks at the long-term positional outcome of a sacrifice of a stone or a chess piece. And here's a famous chess game that was played, and here was the sacrifice of a bishop, which then led to winning the endgame in this case. Now, very briefly about Go. It's 3,000 years old, 40 million players at least, and it has 10 to the 170th power of positions, which is more than the atoms in the universe. So that is the complexity that can be achieved in this very simple looking board game. So here is a rule of, again, you capture the stone by putting your piece here, and you can take the white stone out. This is a score of 1. And here you have the white territory, and the black territory is marked out, and you count the squares, which is your final score at the end of the game. There are 2 neural networks involved. One, the policy network, which looks at the likelihood of a move that should occur at this time, and a value network which calculates the probability of this particular move leading to a win. And these 2 networks are combined and perform the AlphaGo game. So here are a couple of the astounding moves. What is remarkable is that the AlphaGo machine did some innovation. Usually there is a rule that you shouldn't play more than 2 or 3 lines inward from the edge. But there is an astounding move in game 37, move 37 in game 2, where AlphaGo went in a lot further, namely I think to the 5th row. And the audience was aghast. What an unconventional thing to do. But AlphaGo went ahead and won the game. So it's not a stupid algorithm, but in fact can come up with revolutionary new creative notions or ideas or thoughts as to what might be the appropriate strategy for winning. Okay, so let's go back again to the beginning. What the brain does is it receives a sensation which leads to an action. This is the primary job of the brain, to look what's in the environment, to perform a computation. What is a reasonable move for me to do? Approach or avoid, attack or retreat, eat or not eat. And all this is computed, of course, here in the cortex. And here's a sketch of a neuronal network. You can see the different neurons connecting with each other, and you have about 100 billions of these neurons in your brain, each of which can have 10,000 connections. So you're looking at trillions of connections in the brain. Well, this is the godfather of deep learning, Geoffrey Hinton. For many years, these neural networks were considered the lunatic fringe because they couldn't really go beyond a certain point of efficacy. But he stuck with it because in an interview he said, I knew we had to use the brain as a model for AI to really proceed effectively into the future. And he tinkered with the system and developed further algorithms which made neural nets effective. So some of these slides are from Geoffrey Hinton that he gave in a recent talk. So he says real neurons are too complicated, just like real molecules are too complicated. But if you want to understand a gas, for example, you can pretend that the molecules are billiard balls. And you can understand a lot about gases if you just conceptualize molecules as billiard balls bouncing against each other. So he's making a collateral reference to physics, namely the theory of ideal gases and statistical mechanics that does not look at the behavior of individual molecules, but rather at the behavior of the total assembly of molecules in a closed system. And here again we have the input vector with different weights assigned, and we need to achieve a threshold in order for the signal to be transmitted into the next layer. So let's say the job is to show the network a RGB intensity values. These are just pixels, colored pixels from an image. And we want to translate these pixels into words that describe the content of the image. So this is the task of the AI system that he wants to use to illustrate what AI can do. So if I show you, he says 3 million numbers, and these 3 million numbers are the RGB values, the pixels of the pixels in a 1,000 by 1,000 image. And your job is to try to compute a program that takes 3 million numbers and outputs a string of words to describe what's going on in the image. How do we do that? And can this be done at all? So what then is an artificial network? We have input neurons here, and we have so-called hidden layers. Hidden layers are not really physical layers. These exist in software. All this is a software program that takes its inspiration from the neuronal network in the brain. So these hidden neurons then transmit these weights in some way and eventually arrive in output neurons. So here again is the information flow in the cortex. Human cortex and mouse cortex, by the way, are very similar. So here the input layer is in layer 4 of the cortex, in pyramidal cells, and then we have feedback coming back to other layers, and eventually we have a cortical output. So you can see there's a great similarity between the AI approach and the brain. And in fact, the AI approach was inspired by the brain. So how do we train a network, an artificial network? There are two basic modules of training. One is supervised training. Show the network an input vector and tell it the correct output. So what the network then has to do is adjust the weights to reduce the discrepancy between the correct output and the actual output. And it can do this over and over again. So you show the image of a cat, and the network needs to compute the image of the cat at the output, show you a cat in fact, and it will not get it correctly, but it can go back into the inner layers, adjust weight after weight after weight until in fact it gets it correct and the image of the cat reappears. And then we have unsupervised training. So you only show the network the input, and adjusting the weights to get better at reconstructing the input from the activities of the hidden neurons is all that is required. Adjusting the weights to get better at reconstructing the input. So he draws an analogy here to evolution. In unsupervised learning, we don't even tell it the answer. We just show inputs, and the answer, we just adjust, show outputs, and it tries to use the hidden neurons in such a way that from the activities of the hidden neurons, it can reconstruct the input. So we have a mutation here, and you can mutate over and over again and select, like in a Darwinian competition, for those combination of weights that recreate your input correctly. What he really added to this model was the backpropagation algorithm, which took some years to develop. And instead of perturbing the weights one at a time, which takes forever, calculus can be used to compute the error gradients for all the weights at the same time. Now here's some deep mathematics, which we will not get into, but for example, with 1 million weights, this is more efficient, of course, than the mutation method by a factor of 1 million. So how to learn many layers of features? So this was the status in about 1985, when things kind of got stuck. And your brain, he says, has 10 to the 14th weights, 10 to the 14th weights, so it's 10 to the 14 times more efficient than the algorithm here in a neuronal network. So we have an input vector that describes, for example, pixels or words in a language acquisition, and hidden layers provide an output, and you compare the output with the correct answer and back propagate a number of derivatives that can then readjust the weights one more time. And that was the revolutionary breakthrough, this back propagation algorithm to make the computation much more accurate and efficient. So each layer of features then has layers of these neurons would learn to be feature detectors for things like edges. And maybe the next day you'll detect a pair of edges joining them at a fine angle. And so that it could be a beak of a bird, or you could get evidence for a beak, and also evidence for an eye, and maybe a feather, and then maybe you think it is a bird. And so the idea is we get a hierarchy of features in this way. And we know that in the human brain, object recognition turns out to be exactly similar to this. In V1, in the visual cortex, certain features of the image are detected, in V2 other features, and eventually the image is composed in higher layers of the visual cortex. This has a corollary to the idea of predictive coding, the idea that the brain does not process the entire image that appears in your retina, but rather only propagates those parts that deviate from a prior experience of the image or a similar image that's already present of your deep neuronal network in the brain. So the predictive coding resembles the back propagation algorithm that is employed in artificial intelligence. So in 2012 then, speech recognition came out, and it was the first killer app. The standard post-processing accuracy for speech recognition was stuck at 23 or 24%. And now it is known that with the backpropagation deep learning nets, we can get the error rate down to 5% or even to the level of human performance. So this, of course, gave a big decrease in the error rate, and all speech recognition now use backpropagation training. Similar for object recognition. So this was done by developing 1 million images that Google or somebody had available that were labeled by humans. So maybe there was a goat in the image, but also a bicycle and maybe a goat herder. And all three items would be labeled by the human. So networks were trained with 1 million images and the correct labels. So that needed to be done, and it only was possible when enough computing power was available and big enough data sets were available to train the networks in this way. Now, the classical AI was stuck at an error rate of maybe 26 or 29%. The University of Toronto, where Geoffrey Hinton worked, was at 16%, and then suddenly, in 2015, something happened. Deep neural nets were at 5%, and that approaches the human performance standard. So here then is an example. The neural net gets to look at this image, and it decides with this level of confidence this is a cheetah. It also considered a leopard, snow leopard, and Egyptian cat, all reasonable guesses. But the top guess, of course, was the correct one, maybe a cheetah. So in this image, the neuronal network diagnosed a bullet train, which is the correct answer, with this level of confidence. It also considered the idea of passenger car. Now, it's not totally unreasonable if you look at this image, but it rejected this. It also considered subway train and electric locomotive. Again, reasonable guesses. Now here, it made a mistake. It says this might be a hand glass. Well, it is a hand glass, but it came up with scissors, and hand glass was in number 2. But you can see the image is pretty close actually to a frying pan. or even a stethoscope. So mistakes still can occur, but the rate of mistakes is dramatically reduced. So now remember, our job was to take a visual image and have the computer say, after it looked at the image, this is a cat, or this is a cat in a cage, or this is a baby holding a teddy bear. So we are not there yet. We are now able to recognize images. We need one more step, and this is the recurrent neural networks that were developed. And they go something like this. The hidden layer neurons now talk to each other. The states of the hidden neurons at any one of these time, we now are in a time domain. When you do speech recognition, you are dealing with time because a spoken sentence occurs in a measure of time. So the states of the hidden neurons at any one of these time slices are determined by the input and by the previous states of all neurons and the weights of those connections. So it's a tremendous amount of connectivity and computation. And with each time period that you go forward, you have a change in the distribution of weights. So each time period you have a new input, and each time period you have a new distribution of weights. So this is a recurrent neural network. So we need this for recognizing language and for machine translation. And the revolution here occurred in 2015. So we need a encoder recurrent neural network and a decoder recurrent neural network. So the encoder reads the sequence of words in a source sentence. And its final state before the output represents the thought that the sentence expresses. Now this is the sentence that captured my attention and was the inspiration for presenting these two talks. Because, consider this, he provides a very precise definition of what a thought is. So we have a recurrent neural network that takes one English word at a time, and it gets to the end of the English sentence and converts that English word into what we call a word vector. So the word has acquired all kinds of connotations by being put through this recurrent network, and all these numbers and weights can be expressed in a mathematical form of a vector. So those word vectors are now fed into the hidden units, and the hidden units over time accumulate information in their state, relating the different word vectors to each other. So then the final state of the hidden units has accumulated information about all the words, and we are now going to call that a thought. So the network has now decoded the sequence of words. It can translate into a different language, but it has also, in a sense, understood the meaning of the sentence because it is equivalent to a thought before it gets expressed. Okay, so let's go on and look at Jeffrey Hinton's definition of a thought. He states, you never saw a thought before. Now, this is what one looks like. In the neural net, there would be an activity vector of the final state of this recurrent net after it said the English sentence. And then to translate, we take that thought and we make it the initial state of the French network. And the French network then takes the thought and sends it through its eternal network and comes up with a French translation. So here we have the input into the French decoder network, let's say, and the English word is now a thought vector. And each thought is converted into a big vector of features that captures the meaning of the word. and then time goes on here, and we have a decoder network. We have the thought input here, and as time goes in, the recurrent network specifies the distribution of possible words for an appropriate translation. So the decoder network makes some guesses at first. It has a probability distribution of what might be the appropriate French word. And we continue this and improve the guesses by running it through the recurrent network until we have a final version, a full stop of the translation. So given a sentence pair, we use backpropagation through time to maximize the probability of producing the specific and correct translation. The system was trained for one pair of languages. It already beats the state-of-the-art on that data. So what would happen if we take the European Parliament, given its 25 stereo translation of thought, and we can backpropagate of all 25 decoders? And that, of course, is going on at the current time. Now, the activity vector that was fed into the language machine is called a percept. Now, the word percept has a long tradition in psychology, and the definition is not really that clear. So, as an encore, Geoffrey Hinton gives us a precise definition of a percept. Namely, it's that what is in the last layer of encoding of all the pixels you put into the recurrent neuronal network. So these percepts then are being fed into the language network. Geoffrey Hinton says, so now what we're going to do is we take the last layer and say that's the percept. And we can take the percept, we map it through a matrix to get a thought. We feed that into the decoder network, and now the decoder network can tell us what is in the image. The idea is you take your network that could recognize objects. You take the last hidden layer of that, and the percept, and you map that through one more set of weights to get a thought which can be expressed in language. So a recurrent network was shown this image, and it came up with this description: a group of people shopping at an outdoor market. Now, the network never had seen this image, and it decoded the image, put it into the language network, found the appropriate words, and then put it together in a sentence. The original encoding by the human labelers for this picture was a group of people crouched around an open market. So I would say that is pretty close. So here the network says a close-up of a child holding a stuffed animal. A young girl asleep on a sofa holding a stuffed bear. So it's almost identical with the labeling done by the human workers before. So what does the network say about this image? Well, it calls it judo. This one I couldn't recognize. It's correctly identified as beef stroganoff. This is Halvella sulcata. Never heard of this plant or mushroom. This is Abronia fragrans. Never heard of it. Scyphozoan. Never heard of it. Oceanfront. I would recognize that, of course. But the key is that this network is able to recognize images that you would have trouble identifying. So now, the key outcome, and the somewhat scary outcome, is this: there are implications for document processing, because a document is just a sequence of thought vectors. So Geoffrey Hinton predicts that soon people will use deep recurrent networks to learn model sequences of thought vectors. And this, in the end, will capture natural reasoning. Computers will understand what a document is saying. Now, we need billions of neurons and trillions of parameters to reach human level of understanding. We are not there at this point, but that is the direction things are going. In the past, AI was inspired by cognitive science, namely, we must use algorithms on symbols, symbol calculations that are precisely defined. And AI was not able to make much progress as this was going on. And they thought that reasoning must consist of manipulating internal symbolic structures using rules of inference, the rules of logic. This is, of course, not what's happening in the brain. So the neuron-inspired paradigm for cognitive science is that we implement neural networks for control of vision and motor control, for example. Reasoning came very late into the picture. Our brains are primarily designed to see and move about in the environment. Processing symbol strings is not done by manipulating internal symbolic expressions. Symbols only exist at the input and the output stage. And here's the key sentence. Inside our brains is just big vectors that of activity causing other big vectors of activity. That is what thoughts are. Only in the very end stage, when you output from the final layer of your cortex, you can express this thing we call a thought in natural language. So then there is a simple theory of how mental language works. We refer to activity vectors in our brain by describing their normal causes or normal effects. So that is why the words we use to describe sensations and feelings are words that refer to things and activities in the external world. I have a sensation of red is shorthand for I have a neural pattern of activity that normally is only caused by red things. So it is logically impossible for somebody to normally have a sensation of green when they look at red things. This has been a conundrum that philosophers of mind have been struggling with, and Geoffrey Hinton just wipes this off the table with this simple pointing out that there's a confusion of language in philosophy. So I feel like hitting Jerry is just shorthand for I have a neural pattern of activity that in the absence of self-control would cause me to hit Jerry. So a mental state is not strictly an internal state. Rather, it's a hypothetical state that is being used to refer to an internal brain state via normal causation. So, the language of thought, or the two causal relations for the price of one, is having a thought does not mean having an internal representation that is a cleaned up version of a sentence, any more than perceiving a red square involves having a red square in your head. AI was dominated by the idea of internal representations of symbolic impressions and operations on them. And AI people just couldn't get over that. Similarly, many physicists in the early 1900s were convinced that you could propagate waves only through a medium such as the ether. And they were very disappointed when the ether couldn't be found. It was Einstein who pointed out that you don't need the ether. It's totally superfluous in his special theory of relativity. So there was a stage in physics where light rays were thought to go through the ether, and of course that is really not what's going on. We got these brains, and these brains do vision and motor control, not evolved for logic. Logic comes much later. They evolved for other things. And they're highly optimized for these other things. And then we have put all this high-level stuff on top of them. And we are not very good at it. But we do it, and of course it's important. So our brains are very good at seeing and moving. And our brains are not very good at thinking clearly. So symbol processing is done only at the top of all the other operations and is not done by having symbols inside your head. Similarly with sensations. And here Geoffrey Hinton comes to a point where he demolishes the idea of qualia, the idea that the feel of a velvet surface or the appearance of a red rose could never be captured by a mere physical system. The so-called explanatory gap, which some philosophers has raised as an opposition to the idea that the brain implements thinking and feeling. So Geoffrey Hinton says, similarly with sensation, I could describe what would have to be in the world for me having this sensory activity vector. So the idea is that I say I have a sensation of red. I'm not referring to something red in my head. Almost everybody thinks we are referring to something inside of our head, some inner thing. But most people think that sensations are these things inside our head, and philosophers talked about this by saying qualia are these magic things you have inside your head. But they are spooky things, but science can't get his hands on it. There isn't any spooky stuff. There's red things out there, and there's this activity in my head that represents that things are red out there, and there is nothing else. Wiping away a whole area of misunderstanding of philosophy and lack of clear thinking of the human mind. So that was a rapid run-through of our first encounter with artificial intelligence. What we learned is that neural networks can be trained. They can be very efficient even without human intervention and human training at the outset. They can do image recognition, speech recognition, speech production, imitate your speech pattern, play all games known to man, including video games, at a rate of efficiency that is much higher than the human efficiency. Artificial intelligence is now everywhere. It's estimated that maybe up to 40% of all jobs that humans currently do can be done by artificial intelligence and probably will be done, raising incredible difficulties and challenges for policymakers and us as humans as a whole. But I think the wave is unstoppable, and we will now consider in the next lecture how thoughts are being processed in the human brain and contrast those findings with what we have learned today from Geoffrey Hinton. Thank you for your attention. We'll see you soon again at Behavioral Health 2000 for another lecture.